All right, time to talk about stereochemistry. Stereochemistry. As you can perhaps envision, the word stereochemistry comes from stereos, which is Greek for three-dimensional space. So in this chapter, we are going to discuss how the presence or absence of certain groups which are directional, either they're pointing towards you or away from you, how that affects maybe their binding to a certain protein. And so it becomes a very, biologically, a very relevant topic. Now, compounds can be classified with respect to this property that is called chirality. And like I discussed, we started discussing this in class, chirality, which basically comes from Greek for chir, for hand. And so when you're thinking about chirality, you're also thinking about handedness. Handedness. And so what that means is if you're referring to, let's say, your left hand, so there's my thumb, there's my index, middle finger, ring finger. Okay, that was not too bad. And let's say I'm looking at my right hand, so I'm looking at my palms. Okay, whatever, you get the point. So if you envision your left against the right, realize that the left hand cannot fit into the right glove and the right hand cannot fit into the left glove. That means the way our hand is directed, the direction that the thumb is pointed, it is going to fit in a certain space. And that is what we mean by handedness. So all chiral objects, they possess this property of handedness. So for instance, if you consider golf clubs or scissors or shoes, you can buy a right hand or a left hand set which fits your hand. So for example, left-handed glove is going to fit in the left hand, that kind of thing. On the other hand, if you consider achiral objects, those do not have handedness. So if you consider something like, and in class we discussed this as, I gave you an Erlenmeyer flask, or if you consider maybe a baseball bat, which doesn't have any writings or logos on it, or maybe a football or soccer ball, and it's just a sphere. So it's the same in each direction. It's a symmetric shape. Or if you consider a pencil, which has the axis going through the lead. And if you consider perhaps a t-shirt, you can divide that into two equal halves. So chirality of an object is essentially related to its symmetry, and to this effect, it is useful in recognizing certain symmetry elements. And that's what I discussed in class as well, that when we are seeking a chirality, there are certain aspects that we have to go by. And the first one in that, from the perspective of any object around you, would be a symmetry element, that it should not have a plane of symmetry, a line of symmetry, or a center of symmetry. So if I consider a plane of symmetry, that means essentially you have something, a plane that divides the object into two equal halves. A point of symmetry would be something that you can draw lines through, and it's going to essentially look for symmetry in both the directions. So for example, if you have, let's say, cards, a deck of cards, and you have maybe the queen of hearts, so that's the queen's head, and then that's whatever its image, and then this one is a little bit on the left side, and then that's the image. And you might think that, well, they are not exactly in the center, so maybe they are asymmetric, but that's not really true, because you can set up a point within the molecule, and you can, have like a line go in that direction, which is going to divide that into two equal halves. So you can have, like I said, a point of symmetry. You can have a line of symmetry, or you can have a plane of symmetry. And if you have any one of these, you would say that this is a reflective symmetry element that is present and that is sufficient to assure that the object will be achiral. So it suffers of achirality. It's achiral. So the point of discussion in class was things like an Erlenmeyer flask, for instance. You can divide the Erlenmeyer flask into two equal halves, and so you would say that that particular object is going to be achiral. On the other hand, if you cannot do that, if there is no plane of symmetry that divides your object, so for instance, if you try to perhaps draw a line through your right hand or through your left hand, the two halves that you get, they are not identical to each other. Even if you consider the right hand and the left hand by themselves, and you try to lift the right hand and put it on top of the left hand, you will probably see something like, like a fish, but it's not going to be symmetric on each other. And that's an important point that I'm going to discuss in the next couple minutes. But realize when we are seeking chirality, we are not seeking symmetry. So we are seeking asymmetry in that case. That means no point of symmetry, no line of symmetry, no plane of symmetry. The other thing that I said with respect to the compounds in question is that we should have an achiral and asymmetric center. And what I mean by that really is that if you have a carbon atom which is connected in all four different sides by different groups, so let's say one of these is an OH, another is a hydrogen, maybe one is a methyl, and the last one is, I don't know, chlorine, bromine, something. So these are four different groups, and we'll consider that chiral, or we'll consider that asymmetric. Usually, if you have to seek asymmetric centers, you put an asterisk right by it, and that will tell you that it's a asymmetric carbon atom. So be prepared to look for some asymmetric carbon atoms in the near future. And another thing that I would want to bring out here is that this carbon that we are calling chiral or asymmetric, it must be an sp3 hybridized carbon atom. That means at any given point of time, you cannot say that a C double bond C and maybe an OH here and maybe an H here. You can never say that this carbon atom is asymmetric. Why? Because the rules of Kahn in gold prelog from the E and the Z, recall, anytime you have a double bond, it's going to be counted twice. So you're going to say, let's say this was a CH2, you're going to say that the carbon in question, it has an OH on top, it has an AH on the left side, it has a CH2 on the right side, and it has a CH2 going at the bottom. So these two are identical, and you would say that that is not asymmetric. It's a symmetric molecule. on the other hand, if it's purely sp3 hybridized and all four groups are different, you would call it chiral, or you would call it to have an asymmetric center. So when you do encounter a carbon atom, a configuration, the configuration of such a molecular unit is chiral, and the structure can then exist in either a right-handed configuration or a left-handed configuration. So if you consider, just like a couple minutes ago, I said that when you're thinking about your left hand, and when you're thinking about your right hand. And now I want you to envision a mirror plane that goes through that. You can perhaps envision that if you take your right hand and your left hand, you compare them, you would see that one is a mirror image of the other. The left hand or the right hand are their mirror images of each other. But if you actually try to lift your right hand and place that on top of your left hand, so when you do that, I want you to, I drew it a little bit funky. This is what it would look like. What I want you to do is take your right hand and put it on top of your left hand. Now when you do that, and I'm just going to put it in a different color so you can see, maybe in red. So now I'm going to place, this is my thumb, that's my index finger, that's my middle, that's the ring, that's the little, that's what you get. That means the thumb of the right hand is on the little finger of the left hand. Likewise, the little finger of the right hand is on the thumb of the left hand. The thumb of the left hand. So when you have this kind of a situation, you can get, like when we were little, we would say, okay, a fish is moving, moving your little finger and your thumb, but they are not matching up. There is like a mismatch that we have. One point of caution here, a lot of people try to join hands and in a namaste type situation and say that, oh, but I found a match. Well, that's not what we call match. A match or a mismatch can only be detected if you actually lift your object and put it on top of the other, all right? And that's what we are going to do for every single molecule as well. You have to lift the object and put it on top of the other object to see if it matches or not. You can't just fold it on top of each other into a namaste type situation and say that there is a match. Of course, there would be a match then. So let's consider, having heard that, let's consider the molecule of lactic acid. Lactic acid. And in lactic acid, I have this carbon in the middle. I have an OH, a carboxylic acid, a CH3, and an H. And if you think about it, of course, these are forming like the sp3 hybridized tetrahedron. All of that still holds true. If you were to draw the mirror image of that mirror image is going to look like OH on top, COOH on the side, CH3 on the right hand side, and H pointing towards it, right? And now if you actually lift this molecule and put it on top of your red molecule, what's going to happen? You will see that OH will fall on top of OH, but COOH is going to fall on top of CH3. Likewise, CH3 is going to fall on top of COOH, and the hydrogen in this case is going to be pointing in this direction. So what can be said about the mirror image of this molecule? It can be said that this mirror image is going to be non-superimposable. So notice we do have a chiral center, we do have an asymmetric center, and the mirror image is non-superimposable. Such kind of compounds which have a non-identical, non-superimposable mirror image, we would say these two forms of lactic acid are enantiomers of each other. Enantiomers of each other. So in that sense, I can say that my left hand is the enantiomer of my right hand. And the reason for that is because it does not contain a plane of symmetry, so it does have chirality, it does have a sense of handedness. In addition to that, since there is a mirror plane that goes through the molecule, and if I lift the right hand and put it on top of the left hand, essentially there's a mismatch. So they do form non-superimposable mirror images, and whenever you can see that, you would call such objects or such molecules enantiomeric in nature. Okay, having said that, let's see if we can apply this concept. Let's see if we can look for some stereogenic centers. There's some carbons, 1, 2, 3, 4, and 5. Hopefully you can understand, you can see here that the methyls, those are all CH3s. So those are not really stereogenic in nature or chiral in nature because they have 3 hydrogens. They are all identical. If you consider the carbon number at 3, that has 2 methyls over here, so that's identical groups as well. However, if you consider this 2, there is a bromine, there is a methyl, there is an isopropyl, and there's a hydrogen. So sounds like there are 4 different groups, and yes, then you can put an asterisk by it. All right, so again, when you're looking for stereogenic centers or chiral centers, stereogenic meaning it has the capability to generate, to get enantiomeric forms. That's why stereogenic. I want you to think about all 4 different groups. It has to be an sp3 hybridized carbon atom, and you will see that you would get non-superimposable mirror images within that molecule. If you consider maybe another molecule, we have Cl, we have a group here. Notice none of the CH2s are going to be chiral in nature. This particular carbon atom has 2 methyls, and sometimes I would draw them as, like a very nice solid and the dash. That means nothing. Still see what groups are connected to those positions, and if they're methyls, both of them are methyls, then it can't be chiral. If you look at the carbon that's holding the Cl, yes, that is chiral, that is asymmetric, because if you go in this direction, you're going to hit a CH2 followed by a CH2. On the other hand, here you're going to hit a CH2 followed by a CH3CH3. So those are 2 different groups. Of course, you have a hydrogen and you have a Cl. So those are 4 different groups, and so that's your chirality. On the other hand, if I had a molecule, let's say, like that. So I have 2 carbons which have exactly the same CH3. Now it's the exact same group, and so you would say that the chirality has been lost, and you do have a plane of symmetry. So a lot of times you would come across molecules which might look as if they have a 3-dimensional sense to them, and they have an asymmetric center, but the moment you start having like a symmetry element, a plane, line, or point of symmetry, you would say that symmetry is lost, and you would consider those as achiral, because if there is a plane of symmetry passing through an atom or a bond, so in this case, for example, it's going to pass through the chlorine atom, and it's going to bisect the opposite carbon-carbon bond, and so you would say that a plane exists which divides the molecule into 2 equal halves, and that is not going to be considered chiral. So remember, all chiral structures will exist. A as pair of enantiomers, must have B, the sp3 hybridized chiral center, and should not have a plane of symmetry going through them. So these are the three characteristics that I was referring to in class that you would look for as far as symmetry goes.